In the previous lecture, we discussed about something called as stability circles. In particular, we saw those stability circles which are drawn on the gamma plane, either the gamma S plane or the gamma L plane, depending on whether you are looking at the input stability side or the output stability side. So, one thing that you should always keep in mind is that those stability circles, for the most part, are for those MMIC amplifiers which are non-unilateral. That is when S12 is not equal to 0. And for unilateral cases, all you need to check for the stability is what is the magnitude of the S11 or S22, because gamma in and gamma out essentially reduce to those. But the question is, in case of non-unilateral MMICs, we saw that even if a transistor or an amplifier is potentially unstable, then by constructing the stability circles, we can actually choose a region where we can choose a source or a load impedance that would ensure stability. So the question is, if a unilateral MMIC is potentially unstable, then what can we do? If a unilateral MMIC is potentially unstable, then what can we do in terms of the source and load impedances to ensure that it is stable? Answer is nothing. Nothing can be done. Because for unilateral MMICs, although the test for stability is extremely simple, the gamma in and gamma out essentially reduce to S11 and S22 respectively. So, as you know, gamma in is S11 plus S12 S21 gamma L divided by 1 minus S22 gamma L, and gamma out is equal to S22 plus S12 S21 gamma S divided by 1 minus S11 gamma S. This is what we know. But for unilateral case, if S12 becomes 0, then this entire second term for both vanishes. So gamma in over here becomes equal to S11 and gamma out essentially becomes equal to S22. So therefore, whatever is the source and load impedance, it just cannot affect the stability. You can verify this in another way also. Suppose we construct the output stability circle. Because gamma in indicates output stability and gamma out indicates input stability circle. Now the question is, what would be the radius of these two circles? The radius RL, if you recall, is given by something like this: S12 times S21 divided by mod of some quantity, that is mod of S22 square minus mod of gamma square, and the radius of the input stability circle is S12 S21 divided by mod of S11 square minus mod of gamma square whole mod. Now if S12 becomes 0, then what happens is that even RL tends to 0 and RS will also tend to 0. However, CL and CS will not be 0, because CL, as you know, does not depend much on, the numerator of CL does not depend on S12. So I'll just quickly write the expression. For CL, it is S22 minus delta times S11 conjugate, the whole conjugate. divided by this, and similar for CS. Now S12 will affect the delta values, but it will never make them 0. So therefore CL is non-zero and CS also is non-zero. So therefore if you were to draw this stability circle, so to speak, because what they are still circles with some non-zero center, the center will lie somewhere on the gamma plane, but the radius, the two are 0, RS and RL, the circles will essentially reduce to a point. The circles will essentially reduce to a point. So therefore, let us say, if I look at the output stability and input stability, so output stability is always on the gamma L plane and the input stability is always on the gamma S plane. Now suppose this is the Cartesian plane for gamma and this is my Smith chart. This is Smith chart, which is nothing but mod gamma L equal to 1. And this is the Smith chart where mod gamma S is equal to 1. Now if I draw the stability circle, essentially if I see there is something like this, what will happen? If let us say the center is over here, this is, let's say, CL, and if the radius essentially becomes 0, then the circle would reduce to a point. The circle would reduce to a point. Now there are some good things about this and some bad things about this also. Going by the discussion from the previous lecture, if the S11 is less than 1, then any point in the Smith chart can be stable. Any point in the Smith chart can be stable, or any value of ZL that you choose in the Smith chart can be stable. But if S11 in magnitude is more than 1, then ideally we choose the region of the circle that is overlapping with the Smith chart. Here that is not possible. So therefore it can never be made stable. Now if this center suppose comes over here, for instance, then what can be done? There are several other possibilities. Likewise, if I say that CS is over here, in case of the input stability circle, and if RS becomes 0, the circle essentially converges into a point. So if S22 now, if this S22 is less than 1, then any point inside the Smith chart can be stable. So therefore, what we see is that ideally we expect any MMIC amplifier to have S12 0, and that also simplifies the calculations a lot. But from the stability angle, it may not give the designer too much of flexibility. So therefore it is always good that we have some amount of S12 that is non-zero. So therefore it is, we would like S12 to be small but not 0. So therefore we prefer transistors or MMIC amplifiers with S12 being something that is close to 0 but not exactly 0, or not that small also. But the problem is, the moment we make S12 as non-zero, some of our calculations essentially become a little bit more tedious. Why? Because the gamma in and gamma out formulae, for instance, they become a little more complex. So therefore, we see that although from the calculation point of view, we want that the S12 should be 0, but from the stability angle, it's always preferred that the S12 should not be 0. So therefore, can we say something like if I somehow have an MMIC that has a non-zero S12. If I have an MMIC that somehow has a non-zero S12, it is good for stability. But if I calculate, let us say, the gain, the power gain or the transducer gain of that MMIC, considering that S12 is 0, even if it is not 0, then how much error are we making in the gain? Suppose I write the expression for the transducer gain. GT, that is this quantity, suppose I write this expression. Now, if I say that even though this is not a unilateral amplifier, but somehow I make gamma in equal to S11 by assuming that it is unilateral, or rather I am forcing that I will consider that S12 tends to 0, then obviously there will be some error. So normally gamma in is S11 plus some quantity. It is S11 plus some quantity. So suppose what we see is that if gamma in is more than S11, which is quite likely, what we will see is that we will get some value of GT. But if I force that gamma in is equal to S11, then what will happen is that I will get something called as GTU, or the unilateral gain, where gamma in will essentially become S11. So that this formula will essentially reduce to 1 minus S11 gamma S whole square times S21 square Now, if we are saying that gamma in is more than S11, then GTU is more than GT. GTU is more than GT. So therefore, if GTU is more than GT, the question that we need to ask ourselves is that if we are approximating the transducer gain into a unilateral case, what is the error in the gain that we are making? Right? So therefore, what happens is this error that is usually in a range. And there is a derivation for this range. I am not showing the derivation. Essentially what happens is that the actual gain, which is GT, versus the unilateral gain, this ratio essentially gives an indication of the error, GT divided by GT. And this, there is a bound for this. It has a lower bound, it also has an upper bound. So the bounds are essentially obtained, again the derivation is not very important. So if you are making this approximation, then we can see that the variation in the approximated gain versus the original actual gain, if we are assuming it to be unilateral, that is something like this. Now this U has a very special name. This U has a very special name. It also has a formula. We shall write it what it is. Let's write that first. U is this. The product of the magnitudes of all the S parameters divided by, so this should be S22, divided by 1 minus mod of S11 square times 1 minus mod of S22 square. This U is called as unilateral figure of merit. Figure of merit, or in short form it's also called as FOM. Obviously, U should be as small as possible. If you want to approximate a non-unilateral into a unilateral, obviously S12 it should be as small as possible. So therefore, U should be as small as possible. Therefore, if U is as small as possible, then you will see the bound of the error would also be minimum. So therefore, the point of the discussion so far is that it is often helpful that we have the MMIC, which is non-unilateral, because it helps us give some flexibility from the stability angle. But from the gain calculation point of view, often it is easier if we consider that to be unilateral. But we must not directly do so. We must see what is the error bound, and thereby we have to take a decision whether to go ahead or not. And we will know that, okay, if there is an error, it is so much, that is governed by the unilateral figure of merit. So, having said all that, let us now consider what is GTU. Suppose we have the MMIC, which is non-unilateral, and we have said that, okay, but we will still assume that the gain is largely unilateral, and let us say we have a small error that is governed by U, and we are happy with it. In reality, there will be some gain which you will get that is different from GTU. But if the error is small enough, it's okay. So let us add some frequency using some S parameters. We will write down what is the GTU, and we already know the expression for that. Right? Now, as you know, this S21 is called as the intrinsic voltage gain of the MMIC. So therefore, this S21 square is called as the intrinsic power gain of the MMIC. This is S21 mod square. Now, I have one term which denotes something on the source side of the MMIC, and this term is something that is denoted for the load side of the MMIC. So therefore, these are also some terms we call as the gain contribution terms. We call this as GS, and this we call as GL. This is called as the source side gain contribution, and this is called as the load side gain contribution. So the question is now, suppose we want our GTU to be maximum possible. Suppose the question is given the source and the load connected to the amplifier. What is the maximum possible gain we can extract out of it? Or the other way of asking this is that, can we design our source and load impedance in such a way that the amplifier can give maximum gain? Well, before we discuss that, you see that the formulae for GS and GL are very similar in nature. GS and GL are very similar. So therefore, they are very similar to each other. So for GS and GL, we will give a term called GI. We will define them as one generic expression, which we will call as GI, that is 1 minus mod gamma I square divided by mod of 1 minus SII gamma I square, where a single I equals S or L because source or load, and double I indicates 1 1 or 2 2. So for source, I is 1 1, for L, I is 2 2. So this is one general way in which we can represent the gain contributions from the source side as well as the load side. So therefore, let us take a general look at this. We just now said that GI is this quantity, 1 minus mod of gamma I square divided by mod of 1 minus SII gamma I square. So when will this quantity become maximum? When will this quantity become maximum, or when will GI become maximum? It can become maximum when the numerator becomes maximum, or the denominator becomes minimum, or both. Suppose I say that somehow I want to make the numerator maximum. Then in that case, so GI will be equal to GI max when, if you notice that if I substitute gamma I equal to the complex conjugate of SII, then the upper term will essentially cancel out. That is like saying when gamma I is equal to SII conjugate. Remember, SII is the amplifier parameter which we cannot change, but gamma I can change. So if gamma I becomes SII conjugate, what that means? That means on the source side, gamma S equals, on the source side, gamma S would equal S11 conjugate, or on the load side, gamma L will be equal to S22 conjugate. Doesn't matter whichever one we are choosing. So when I do this, what will happen? Substitute this, you will get gamma I equal to S11 conjugate, but the mod will always be the S11 or SII conjugate divided by 1 minus mod of SII square, the whole square, because now SII and gamma I will get multiplied and will be complex conjugates of each other. So the product essentially is mod of SII square. So this term and this two will get cancelled, which means the GI is now 1 minus mod of SII square. This is GI max. So therefore, if I want to write GS max and GL max, all I need to do is substitute it with the proper S parameter. So GS max will be 1 minus mod of S11 square, and GL max will be the 1 by 1 minus mod of S22 square. Now, in the transducer gain equation, there was this term called GO, which is the intrinsic gain of the MMIC. This one cannot be changed, as it is mod of S21 square. Mod of S21 square. So therefore, I can write GTU max that will be equal to GS max times GO times GL max, and that is equal to one by 1 minus mod S11 square times G0 times 1 by 1 minus S22 square. So therefore, if I have an MMIC which is almost unilateral, this is port 1, this is port 2. Now, if I have to get the maximum possible gain out of this MMIC, all I need to do is, if the reflection coefficient gamma in is S11 now for unilateral, and the gamma out is equal to S22, then all I need to do is connect a source of impedance ZS that will be equal to Zn conjugate, and I have to connect a load. I have to connect the load ZL, which should be equal to Z out conjugate, where obviously, as before, gamma in and gamma out, the formula is standard, Zn minus Z0 divided by Zn plus Z0. This is Z out minus Z0 divided by Z out plus Z0, where Z0 is the characteristic impedance of the port feed lines. This is how we can get the maximum possible gain out of our required MMIC. Now, apart from the maximum possible gain, often it is not desired to have the maximum possible gain. Rather, we would like to use the MMIC to achieve the gain that we want. Often, or rather most of the time, we usually want some pre-decided value of gain which is often not equal to the maximum. So, the question is, suppose we want some gain that is obviously below the maximum possible, then what can we do on the source and the load side to ensure that? Obtaining some desired gain value. So let us say we have this GTU that is equal to GS times G0 times GL. Obviously, we cannot touch G0. We need to do some manipulation at the GS side or the GL side, or both. Suppose my load is fixed. Then GL, I cannot do much. Or suppose my source side is fixed. Then GS I cannot do much. All I have to do is do something to GL. So if one side is fixed, the other side is not fixed, or both sides are not fixed, then we can play around with the values of GS and GL. How? This GS and GL are decided by gamma S and gamma L. So again, just like stability, we can judiciously choose some values of source impedance and load impedance in order to obtain the gain that we wish for. How? So GS, the general formula is this: 1 minus mod of gamma S square divided by mod of 1 minus S11 gamma S square. So S11 is fixed, but we can play around with the gamma S value and get different values of gain. For different values of gamma S, we will get different values of gain. Likewise for GL, which is this, we can play around with the values of gamma L and get different values of GL. So therefore, the conclusion is we can tune the GT, right? So to do this, we know that generally the upper bound of GS and GL is there. So obviously we can get GS below the GS max. Likewise, GL we can get less than or equal to the GL max. So since GS max and GL max are the maximum possible gains contributed by the source side and the load side, what we will do is that we will essentially represent this in a normalized fashion. So we will call this as small gs, which is nothing but the actual gs that we want divided by the gs max. Likewise, small gl will be the gl that we want divided by the gl max. So gs, as we know, is this. This whole divided by the gs max, which is 1 by mod of 1 minus mod S11 square, which will come again in the numerator, which will be 1 minus mod S11 square. Likewise, the normalized GL will be 1 minus mod gamma L square divided by mod of 1 minus S22 gamma L square times 1 minus mod S22 square. Yes, I think this is, yes, that's correct. So now we say that we want to fix GS. We will fix GS, we will fix GL into the values that we want. GS max and GL max are already fixed. We cannot change because they depend on the S11 and S22 respectively, which we cannot change, of the MMIC. Now, if we are fixing GS max is fixed. If we are fixing GL and GL max is fixed, what we are seeing is that GS and GL are also fixed. So this small gs and small gl are fixed. So therefore, now the question is, S11 is fixed here, S11 is fixed here, S22 is fixed here, S22 is fixed here. So if we say that gs, which is fixed, and gl, which is fixed, the only variables in these two equations are gamma s and gamma l, respectively. So therefore, just like the case of stability, we will try to isolate gamma s and gamma l as one term and group all the other terms together with some analysis. So therefore, again, there is some analysis using these complex terms which is beyond the scope of our discussion. So we shall not go into that, but rather I will show you what the result comes. So if you rearrange the terms, what you will get is something like this. Mod of gamma s minus gs s11 conjugate divided by 1 minus mod s11 square times 1 minus gs whole mod is equal to root of 1 minus gs times 1 minus s11 square divided by 1 minus mod s11 square times 1 minus gs. This is not a whole multiplication, so just be careful of that. This is multiplication only with s11 mod square. Likewise, here we will get mod of gamma l minus gl s22 conjugate divided by 1 minus mod s22 conjugate times 1 minus gl whole mod is equal to root of 1 minus gl times 1 minus mod s22 square divided by 1 minus mod s22 square times 1 minus gl. Very equivalent relationships between the two. So once again we see that the form of these equations are familiar to us. So I can say gamma s minus CGS. This indicates for the normalized GS equals some RGS. Here gamma L minus CGL mod is equal to some RGL. Once again, we see that these two are circles. These two are equations of circles on the gamma S plane and the gamma L plane respectively. Gamma S plane and gamma L plane respectively. So it is all coming back to us in the form of circles. So therefore, let us again write them down. We will call them, these are called as gain circles. We will call it as source gain circles, and then we will call this as load gain circles. So the equation is the first equation is gamma S minus CGS equals RGS. Do not confuse this with gate to source capacitance, that is a different thing. This is gamma L minus CGL is equal to RGL. So now we have to construct JV, this is U. We construct the Cartesian axis. This is the gamma S plane. This is the gamma L plane. So if whether or not you draw the Smith chart, that's a different thing. You will get one circle whose center with respect to the origin will be CGS and the radius will be RGS. Likewise, over here, we can have one circle with respect to the origin. This will be C, G, L, and this distance is R, G, L. Right? It may or may not intersect with the Smith chart. That is a separate issue. We can verify it once we have the Smith chart with us. So, having said this, let us look a little bit more closely at these gain circles. So therefore, let us look at any of the gain circles, either GS or GL. Let's go for GS. We can choose GL also. So the equation comes out to be something like this, where the center CGS is this: GS times S11 conjugate divided by 1 minus mod S11 square times 1 minus GS. This is the center. Now, let us suppose we take different values of GS. We take different values of GS. What will we get? Can we observe a relationship between GS and successive CGS for those values of GS? What we see is essentially the CGS equation has a GS term in the numerator and the GS term in the denominator. So therefore, if I open this, what I will get is it is GS S11 conjugate divided by 1 minus mod S11 square plus, this minus into minus will become a plus, mod S11 square times GS. This is a constant. So again, we can write this as something like this, divided by some K plus, what we are seeing is that this has a GS term of the first order on the numerator and one term of GS of the first order in the denominator. So essentially this is again a bilinear transform. If S11 is fixed, this is the only complex quantity. Its phase would never change because it is a parameter of the MMIC. So let us say we get different values of CGS for different values of GS. So on the complex plane, if this is my gamma S plane, let us say for different values of GS, the phase will never change. It's a complex quantity. So one CGS may be here, one CGS may be here, one CGS may be here, one CGS may be here. This angle is nothing but the phase of the S11 conjugate. Other all terms are real. So therefore, for different values of GS, all the CGS, the centers of the gain circles lie on the single straight line. So all the centers of the possible gain circles are collinear. This is an extremely important result. You will see that unlike stability circles, there can be multiple gain circles depending on what is the value of GS that you want or that you choose. So, but for different GS, the center of the circle, all of them, those centers possible, will lie on one straight line. So in this particular lecture, we discussed a little bit about the continuation of the stability aspect of MMICs. We discussed that from the stability angle, it is important to have non-unilaterality, which will give some flexibility to the designer. We need S12 not equal to 0, but for gain calculations, we would prefer if S12 is equal to 0, the analysis becomes a lot easier. So therefore, to compensate for the error, we defined a term called as unilateral figure of merit. The smaller, the better, which indicates the error between the unilateral gain versus the actual gain. And from that unilateral gain, we discussed something called as the gain contribution of the source side and the load side. And using those, we saw we can achieve our desired values of gain by constructing something called as gain circles. The point of drawing the gain circles is to show a locus where we can choose any point on the gain circle. We can choose any point on the gain circle, either the source gain circle or the load gain circle, and over there we will get the desired value of gamma S or the ZS, which will give us the desired source side gain or the load side gain contributions. Thank you.